bought a VNA. Now what? And that's Carl Culp, who is up there in my picture is kind of over that way, but he might be in a different spot on your image. And Carl can allude from there about what a VNA is and all the different ramifications of that. And Carl can introduce himself and tell us anything he wants about himself first. And his call sign is AE0DL.
Well, it is now.
It is now.
It started out about 1955. I got a novice ticket at the ripe old age of 11, I think. And I was KN3KQR. And in those days, the novice license was good for a year and it had pretty limited capabilities, privileges, I should say. And I spent most of my year studying and learning the code and doing well. You had to pass a 5-word per minute code speed test to start with. And I think technician was 5 at the time. Is technician still 5? No, technician is no code, right? When they got rid of that, what was the code speed for technicians before they eliminated it?
It was 5, and when they eliminated it and then ultimately got rid of it across the board, it's no longer required. So
sure. Well, I got my general before the end of the year and then kept that call K3KQR during college. And I didn't really do much with ham radio after college. I got a job in a technical industry and really didn't need it. And about 5 years ago, my brother got his ticket and started twisting my arm to get back into it. And I had all my stuff. And I finally went down and took the technician test, which gave me the general. Actually, they give it back to you if you can prove that you had it. And then I did the extra test at the same time. My professional career has been pretty well all in electronics and computers. So I'm pretty experienced with all sorts of technical stuff. I did all kinds of digital and analog circuit design. I did IC design. I worked in the IC industry, both at Honeywell and at Fairchild for a lot of years, and then kind of migrated over into the software arena. So I've been doing software, primarily servers, for about the last 20 years or so. But at any rate, back into RF and into ham radio. And one of the newer developments that we didn't have long ago was the VNA. They were around. They had very expensive ones have been around in a professional arena, but having one that's affordable is more or less a new thing. And it can be very confusing because if you look at the box itself, it isn't obvious how it works. And there are lots of YouTube things. And in fact, before I'm done, I'll mention some of the YouTube resources available because they're excellent. But I would like to sort of level the playing field for everybody. So can you see this thing in my camera? Does everybody see that? Oh, okay. Well, if you want to look at this thing, it should be pretty familiar to you. And it's an old style VOM. And it says right on the top, ohms. What I'd like to do is get everybody familiar with the idea that the measurement that a VNA makes is quite analogous to what this thing does when you're measuring ohms. If you think of it as impedance, then that's what the VNA does. The ohms of impedance happens to be the real part of the impedance to electrical flow that a VNA measures across a frequency range. So if you consider the voltmeter or the ohm meter, that's one end of the frequency spectrum. That's the end at DC. The VNA is useful way up depending on whose you get and what you pay for, but most of them are good to up to a gigahertz or 2 gigahertz or 3 gigahertz. And if you have the funds, you can buy one for 10 or 20 or 40 gig too. For us hams, it's probably not important that they go much above 1 because we don't do too much above 1. Occasionally people do, but most of us are much more interested in things up to 30 or so megahertz for HF, or we go up to 50 or 144 or 220 or 100 or 440. And so a gigahertz is more than enough. So if you ground yourself in the idea that what the VNA is really trying to tell you is what the impedance is, and that can be very closely compared to the resistance in a DC situation. So what I want to show you, let's see if we can't. Now I need to show my screen to do this because I have a camera on my VNA that I would like to show you images of it. All right, that's pretty good. I won't touch it. So one of the problems with these blasted things is you don't know what you're looking at. And it shows enough that it can be quite confusing. So what I suggest for most people is you begin by going in and shutting off a couple of traces. And to do that, you can go and select them as being on or off. Let's do that. Let's just go to 1. Now it's going to be a little more evident what's going on when you're only seeing 1 trace. Now the next thing you need to do is choose a stimulus. And the stimulus, and by the way, I'm using a stylus, which is another handy thing to do on the VNA, especially the smaller screen ones. The stylus of some sort makes it an awful lot easier to select things. So if we go to stimulus, and now one of the ruling factors of VNA, these inexpensive VNAs, is they don't take many points to sample. And if you don't have a lot of sample points, then they have to interpolate between the points that you choose. And the big issue there is that there are gaps, and those gaps are often large enough so they skip over large parts of the frequency spectrum that you might be interested in examining. So let's say you wanted to do an antenna. That's what we decided to talk about. And that's a 20-meter antenna. So anything above, say, 20 megahertz is completely out of scope. And so what we'd like to do is concentrate the samples for the calibrations into the range that we want to look at. So if we look from 10 to 20 megahertz at a 20-meter antenna or 14 megahertz, then we'll get 200 samples in that 10 megahertz range. And 10 megahertz divided by 200 is about 50 kilohertz per step. Even that's a little bit crude, but at least we can make a nice curve. I don't have a 20-meter antenna handy right now. I do have a 2-meter antenna. So let's pick a range and calibrate for measuring a 2-meter antenna. So if we were to measure from 120 to 170 megahertz, that would be more than enough. So let's try that for starters. So if we click on a start frequency and we put in, what did I say, 130? 130 megahertz. And we want our stop frequency to be 160 megahertz. Now it's going to ask us to put in our open, short, and load values. And so we go to Calibrate, and we want to pick a standard calibration. First, we click Reset because we have to clear the values that are there. And then we got to pick Calibrate. And then we pick Open. So we calibrate the open. That gives us our base open value. And it should run them for a moment here and then show us a check mark on open. All right, there's the check. You see it? That went through the values as an open. Now we got to pick a short, and I'm going to put a short between my terminals here. We'll pick short. Now we're calibrating the short. Then we'll pick on the load when that's done. So what's measuring the values at 200 or 201 points across the frequency range that we picked. All right, that's open and short. Now let's put in the load. Where did my load resistor go? I thought I had that right there.
It's up on the right-hand side, just of the VNA. I can see a resistor there.
Yeah, that's the one I was looking for. Thank you. Now what I'm using for a test fixture is just a couple of vector pins in a little piece of circuit board because I want to be able to show you some components in here. So there we'll pick the load.
Is there an indicator that is showing that it's in calibrating process?
No,
Okay.
it will show us that it's got the calibration over on the left-hand side. It says short open and load. And the L just came up when the load checked off. Okay, so we could make measurements now because we're calibrated over that frequency range, but let's look at a few other things before we do.
Can't quite see what you're doing there on the connectors, but it looks like a 2-port VNA and you're doing an S11 here.
Yes,
So you're on the one of the ports, you're only
calibrating for an S11.
right. So, and that's on the picture here, it looks like you're on the port on the left side, I think, then, right?
Yeah, this VNA has port 0 on the left and port 1 on the right. Same as most of the nano VNAs. This particular one has a larger screen and N connectors, and I have an adapter on this to go to a test fixture. Oh, I can show it to you.
Oh, okay. Yeah, that's helpful.
Yeah. It's hard to get a balance to be able to see all the stuff at the same time and see the screen. But what's in there right now is that 50 ohm resistor. So let's look at that before we go on, because you have to know your starting point. So I'm going to click done. Once done, we're going to save it. So let's save that at number 6. We can come back to that anytime we want to. Now I can see in there a few little glitches. It may have hiccuped a little bit. See that little glitch toward the middle? And it helps to look at this thing before you move on, because if the calibration isn't good, then you haven't learned a great deal. And you may get erroneous measurements. So let's look at the screen. And if you look up at the very top, and that doesn't look very well focused. What we have is log mag of reflection coefficient. So we see a 39 dB reflection coefficient, or loss, if you will. What that means is that if you think of the device as the generator and the device under test that has a load, and we're measuring the signal reflected back from the load to the generator. So if it's a perfect match, how much is going to get reflected back? Nothing, exactly. And it's 40 dB down from our transmitted signal. So that makes sense, doesn't it? We should have a very small signal coming back. So let's put in something else there. let's put in a short. Anybody got an idea for me what we're going to get back from a short?
Almost everything.
Most everything. And you can see we have about 0.8 dB loss. So almost everything. How about an open?
Same thing.
Same thing. Everything gets reflected back. So you can immediately see by just plotting one graph, not letting the whole complicated picture be confusing. It helps a little bit. Let's try another thing. I'm not going to tell you what it is. But you're going to tell me what it is.
How many dB is that?
It says 11.54. Hard calculation to do in your head.
Well,
But you can see that from the frequency start to stop range that we picked, it doesn't change much. So that's telling us it's pretty much a resistive loss.
right.
Okay, it's not frequency dependent. And it's a resistor. It happens to be a 30 ohm resistor. If I were to put a high value there, it would do something similar. Here's a 240 ohm. Different number, it's about 4 dB. That's a 240 ohm resistor. So that, by looking at those loss numbers, we can kind of judge how the component behaves over frequency. So let's do something a little bit more sophisticated. Let's bring up another chart and let's bring up another trace. Now I got trace 1 turned on. Now it happens to be set for S21, which we don't want. We need to set that to what do I do here? I don't want to go there. Come on.
Hey, Carl,
Yes.
maybe I missed this earlier, but when you have that resistor on the port 1 there, how do you have it clipped in there, or how are you making that connection to
I'll show it, then you can see it too. My VNA is not behaving here. Let's go back. We're on trace 2 now. I'm going to set it. It by default came up as on channel 2 for an S21 measurement. We don't want that. Okay, now I got it on S1. Now I want to change that to
I just saw S11 there.
pardon me?
I just saw S11.
Yeah, trace 1 is selected if that's what you're looking for. If you want trace 2, you're on the wrong trace.
Well, I had on trace 0 and trace 1, so I think we're okay.
There you go.
Okay.
Trace 1 is what I wanted to set, I think. And we want to make that one of the values that we can choose. For instance, let's just, we don't want log mag. That's what we got on trace 0. So let's put in the reactance. And now it's going all over the place. If we put in a resistor like we did, and I'll show you this so you can see it too. I'm going to put the 50 ohm resistor back. So what I've got is that the 50 ohm resistor, just we're looking down on some vector pins. These are vector pins here. And the resistor is stuck in between them. And as you can see, on the bottom, the blue scale, it's it's showing us it's about minus 0.2 point something ohms of reactance. Oh, there we go. Let's get it in. There we go. Now it's measuring essentially 0. Let's put in a reactive component now so we can get an idea how that component looks. And then we'll get to our antenna after that. I'm going to put in this little cap. So that's at this frequency from 130 up to about 160. It's on trace 1, the blue one, and it's saying trace 1, S11 times 100 is minus 17.6 or 06 ohms. Now it's not changing a lot because the frequency range is limited, but we got about 17 ohms of reactance. Negative means it's capacitive reactance. If we put an inductor in, we should see something that looks more positive. Let's see what I've got here real handy. Let's put this thing in. By the way, we could have calculated the capacitance value pretty easily knowing the reactance value. And I think if we brought up the Smith chart, it would actually show us the capacitance value directly. So there's an inductor on there. And you can see that that has
a varying reactance depending upon the frequency.
yes, it does. But we're not swinging the frequency a whole lot, so we don't see a lot more, but there it is. And that now, that should be showing us a positive number, not a negative. Am I connected good? That could be this. It's a big powdered iron ferrite. It may be more capacitive than inductive at that frequency. I'll get a better inductor. Something I know has a nice value over that frequency range. Got to be a little careful of that because that inductor I had, I'll hold it up to the camera. Can you see it on the camera? That's a powdered iron toroid about 1.75" diameter, and it might have been more capacitive than inductive at that frequency, but this one probably won't. This is a nice thing.
Hey.
Somebody shit. Or farted.
Well, I'm going to give up on that. It's not making a good connection, and I'm making you guys sit through a nightmare here. I'm going to put on an antenna that it happens to be a 2 meter and 440 antenna, and we should see it peak in the 2 meter range. So can you see this in the camera? It's one of those dual band antennas. It's a magnetic base with a 440 section and a 2 meter section. Let's put it on here. All right, that should look a little more interesting. And you can see it first, the dip in the log mag curve. That dip means that the reflection gets less and less and less when you hit here. So let's look at more characteristics of that. Let's put that.
Hey, how are you grounding the magnetic base on that antenna?
It's just stuck on the side of my computer.
Ah,
And it's obviously not ideal, but
gotcha.
the case of the computer probably gets to the AC ground somewhere. So
Okay.
it's good enough to work. Don't have much of a choice here. So
Yeah,
we're
I
going to
was
go to,
wondering.
pardon me?
I was just wondering, yeah.
Yeah. So let's take trace 1 and let's put that on SWR. Now that's what most people in ham radio like to look at. And we can drag a cursor down there to that null point. And I'm just dragging the cursor
Wow.
with a stylus. And as I recall, this antenna has a pretty low 2 meter SWR. And you can see it's about 1.14, 1.18. So now let's talk about how this compares to what we do with an ohm meter. So at DC, obviously the antenna would be an open circuit. As we excite it at frequencies closer and closer to its resonant frequency, it becomes closer and closer to a 50 ohm load. And what that means is that the 50 ohm impedance of the generator is matched by the 50 ohm impedance of the antenna, and all but a tiny fraction of that signal is being absorbed by the antenna and therefore probably radiated. So that tells us this antenna does half a decent job at 2 meters. Let's put on a different 2 meter
I have a question.
antenna.
So what's the frequency 138.756?
This particular antenna has its low frequency, its lowest SWR at about 138.
Okay.
So a little low for the 2 meter ham band, but if you're interested in what it is at, let's say 145, and the question about grounding is important too. It's going to change a little bit with different grounds. It happens to be mounted horizontally right now. I can turn it vertical and see if it matters. And it looks like it makes a little difference. Looks like it went away. I don't know why that is. That's kind of odd.
Yeah, I don't think you're grounding it anymore.
No, I'm not. And I don't have a good way to get it. I think I'm going to go to my other antenna. There are no radials or anything on this.
This might be a good way to check to see if that pizza plate or pizza pan works okay as a
Sure.
ground plane.
You bet. The immediate feedback to show you what's happening is awfully nice on the VNA because it's telling you in real time what it sees. I have a couple different 2 meter antennas here that you might find interesting. So this one is a bit of a compromise antenna. It is not really exactly 2 meters. I made it a little bit low because I'm close to Crystal Airport and I wanted to be able to pick up the aviation frequencies. and they tend, the ones I'm interested in are down around 120. So it's a little bit lower than an ideal 2-meter antenna would be, but let's put it on and see what it shows us. Now this one is a quarter wave vertical. You can see that it's very obviously got a sharp null in the log magnitude. Let's pull this down and take a peek at it. And our lowest SWR point is at 150. Well, that's odd. The last time I looked at it, I thought it was at about 130, but whatever. Now this particular one is a quarter wave vertical stub, and it's got 4 radials, and the 4 radials are angled slightly down. I can show it to you if you want, but I don't think you can see it too well in my pictures anyhow. But let's do a little bit more advanced thing. Let's look at this thing on the Smith chart. I think you'll find that interesting too. So we're going to go back to our display. We're going to turn on another trace. It's now the green trace. Looks like it's already on Smith because it came up on a Smith. And let's look at that. So now we're pretty much at the low SWR point, but I want you to look at the marker that's on the green trace. Look, follow this marker right here. Now our Smith chart 50 ohm point is right there, and you can see the green trace comes through it. And if we change the frequency, and it's going to be very close to the low SWR point, you can see right, oops, jump right over it. Well, right there, close to that. So at very close to 150.027 megahertz, we have an SWR at 1.07. If you look, if we go all the way out to the frequency extremes, we can see this sweep starting right there. That's the high frequency end, right down right here is the high frequency end of the sweep. It comes around and makes this little loop, goes almost exactly through the 50 ohm point. Then it comes back around and around and around out to here. And so we can move the marker and see that occur. See that number 1 swinging around there? Should be able to drag that marker. You see that moving? So where is the point of lowest SWR? Is that at the point of resonance, or is that the point can be a little off resonance? Well, in this case, it's almost exactly at resonance. And resonance is the point where the green line crosses the center line. So this line right here on the Smith chart is the center of the chart. If you look at the big circles out here, you can see that the chart goes inductive toward the top, capacitive toward the bottom, and resistive on that single line in the middle. And the point where your impedance curve crosses this line is a resonant point. Now, it might not be the lowest SWR point. In this case, it probably is. It looks like it goes almost exactly right through it. But it's telling us that down here, that's the lowest SWR point, and we're almost exactly right on it where it's resonant. Now, if we look at a different antenna, we might see something slightly different. And I have a tight BNC connector that I can't pull loose. All right, let me get down another one. This one is a 2-meter J-pole, a homebrew 300 ohm twin lead 2-meter J-pole. Which you can see behind me, it's hanging right here. Do you see that in the picture? Coax is soldered on the bottom. Oops, wait a minute. Sorry, I lied. That's a 440 J pole. Where is my 2 meter J pole? Well, let's just look at this guy. So now we would, in order to see this antenna properly, we really should recalibrate because we didn't calibrate up in this frequency range. I don't know. Do you guys want to take the time to recal quickly? I have two 440 antennas that I can show you. Yay, nay, anybody care?
Go for it,
Sure.
Cal.
Yep, go for it.
Okay, I hate to make you sit through something that's unpleasant. All right, so let me show you what I did for my BNC cal kit.
You already saved the cal for the 2 meter, so you could probably save this cal over a different range, right?
Oh, absolutely. Absolutely.
Right.
We'll do that. I put that in number 6 or something.
Yep.
So
no harm done at all.
oh no, we'll still have the other cal. You're exactly right. So here's what I did for a cal kit. Can everybody see that? I just took some BNC tees and I sawed them apart. This happens to be a standard BNC 50 ohm terminator. That's my load. This one is a standard BNC T that
I thought if you put them sitting on top of your VNA, we can probably see them better in the screen.
yeah, you're absolutely right. Okay, there's a BNC T with a saw and a little patience. You can saw that part of it off, and that's my open with another one of those and some solder. That's my short. And then the standard 50 ohm terminator is my load. So let's run that cal. I'm going to put the short on and let's go from 420 to 460 or something like that. Does that sound reasonable? And I'll leave the same display because that now we've gone through it in a way which makes all the curves make some sense, or at least a modicum of sense. We're going to go to calibrate and we're going to go, I got to do a reset here. Reset all, reset. Okay, now back and we want to go to calibrate.
Don't you want to go to stimulus to change your frequencies?
Oh, yes. Thank you. How many times have I done that? Calibrate over the wrong frequency range. You're absolutely right. So we want our start frequency to be 420 megahertz.
Aren't you missing a puppy? We're missing a puppy.
Is that for me?
Open mic.
I do have some puppies here, so I was wondering what was going on. Something happened here. I didn't do something right. Calibrate. My screen is funny.
You've got top and bottom set to 420.
Yeah, but my screen went gray here in the middle. Oh, you know what it is? I bet it's running out of batteries. I started to tell everybody that I had a problem with my VNA. It's a very nice product, but it's typical Chinese manufacturing, and the USB connector to charge it fell right off the board. And I think it's done now because this blank screen isn't right. Let me turn it off once and restart it. I have a couple of other VNAs we can use. So if it doesn't want to work, we'll move on.
I was going to say, try checking your stimulus because it was showing both start and end at 42 or 420.
And I clearly screwed that up. Looks like it's working. So start 420 megahertz. Stop. 460 megahertz. Calibrate. Huh. They shouldn't be checked.
Do you have to tell it to reset the calibration
Yeah, I thought
frequency?
I already did.
Try it. Go back to that screen. It said in Calibrate, reset channel range.
Yeah, it cleared. I had to just hit the
Okay.
reset. Okay, there's
Sure.
the open. Okay, there's open. There's short. You'll be able to see on the left, it'll pop up and it'll show the short. There it is. Now it says short. Now we're going to put on the load. This is a different calibration set. The first time I did it with those components because I wanted to leave that little component pins on there. So now we're going to do load. The two antennas I want to show you, the 70 centimeter antennas. One of them is the J pole, which I'll put on right now. Oh, let's take a peek at this. Let's see if our calibration looks valid. And so what we should be seeing is something like a 50 ohm load right now. So on the yellow trace, we're seeing 25 dB insertion loss there or reflection loss. In the green trace on the Smith, we see a dot that's pretty close to center. If you look right here, it's pretty close to center. And then on the purple trays, oh, I got phase on there somehow. I don't want that. Display. We want SWR trace. That one was on blue, I think.
You got trace 3 on as well.
Yeah.
That's the purple. There you go.
Now, trace 1 is on. Format for 1 is going to be SWR. I think that should be working. And SWR on a resistor is real low all the way across. On our log mag, we have about 25 dB, which is good. And on our Smith chart, we have a single point in the center. So that, again, is pretty good. It's telling us that that is a good 50 ohm match. And since it's a 50 ohm load, it ought to be a good match. Okay, so this one is the J pole. Once again, homebrew J pole. It's just a 300 ohm twin lead. And as you can see, it looks pretty reasonable. You can see that it's a little bit low. Well, it looks like as it swings around, it gets a little bit better. So let's pull the marker down to the low point in the reflection, or the low SWR, either one. And you can see that that point is the closest point to the center of the screen right here is approximately where that green trace crosses the axis. And it happens to be at 42.6 ohms and 138 picofarads or something close to that. And the SWR is, well, something wrong with my SWR plot here. I bet it's on the wrong channel. Trace. Yeah, we're on the wrong channel. Here we are. The thing defaults that particular trace to an S21 measurement, so you have to remember to go back and switch it. There we are. We've got an SWR of about 1.176. You see that, or 1.2 up there. And you can see that the thing sweeps from here right around, comes around and goes out there. That actually, the beginning should be up here. They almost always sweep clockwise. So that's the J pole, and it's a pretty decent antenna. I have another one that you might find interesting. And that one might be interesting for a slightly different reason, because it's got a pretty long piece of coax on it. And you'll be able to see the effect of the coax feed line. So can you see that antenna back there? Can everybody see that thing? Maybe a little hard. It's a 440J pole built with copper tubing, but it's got a phasing section in the center and then another dipole section. So it's a coaxial dipole with a phasing section in the middle, all homebrew, but let's plop that on there and you'll be able to see that what happens when you have a feed line is you get the impedance characteristic going around in circles on a Smith chart. Oh, there we go. Now, can everybody see that okay? Here's our low SWR point. So that has about 1.1 roughly. Notice now that the lowest SWR point is not really quite at resonance, because resonance would be where the green line crosses over the center line, but it's actually a little above. I don't know if I can get that any closer. And that's pretty close. Maybe it is pretty much right on the line. 1.087, does that say? And it's 45.98 ohms at 445 megahertz. So antennas are really, really easy to see on the VNA, as long as you don't let all the squigglies on the screen blow your mind, and as long as you do a good calibration. Questions? Pretty quiet.
How important are the calibration fixtures that you have? I have a FieldFox VNA, and the cal kits on those things are crazy priced. And I just use a couple of resistors here, and a low and a short, and I think I've paid $800 for a cal kit for the FieldFox cal kit.
Well, I feel your pain. They are quite expensive, and I can show you what I have. My VNA that came with the N connectors came with an N calibration kit, and I'll show them to you. We didn't use them. We could have today. But one issue is what connectors you're going to use to connect to your device under test, and if you have N connectors throughout, N connector calibration kit makes a lot of sense. But if you've got BNCs or SMAs, or if you've got components on wire leads or whatever, then an end connector isn't too suitable. You got to somehow get that to something you can use. Here is my, I'll put it right here. Yeah, that works pretty good. That's my cal kit for N. And they're all nice end connector things. And that one says load. That one says open. That one says short. And so if I'm going to do something that has end connectors on it, I undoubtedly would use those. I have a homemade cal kit that I showed you for BNC, and I have a lot of stuff on BNC. So for me, that's handy. And I've built up a lot of things that have BNC connectors on them. The other cal kit I have is a commercial one that comes with the nano VNA. And that one is the, they got pushed around here somewhere. Well, I had them on the bench here.
So I guess the question is kind of what big difference is there between the commercially made high buck cal kits, like in the case of your N1 and N type, compared to maybe an N type cal kit that you made yourself and just made it open and a short the way you would do it? Do you notice a noticeable difference in the results when you're looking at the VNA?
Certainly not below 100 megahertz, or not the quality of your cal kit is mostly noticeable at very high frequency.
Okay, right.
There is these are the calibration that come with the nano VNAs, and most of those nano VNAs have this little sit with them. I would guess that up to a gig, this kind of cal kit is more than adequate, especially for ham radio kind of purposes. If you're looking for antenna resonance or something,
Probably the only thing you really want to worry about is that load. You want to use a carbon resistor as opposed to a wire mount.
Oh, absolutely, absolutely. And the one I showed here, this guy, the 50 ohm cable terminator, in the days of coax Ethernet, those were very common because your coax 10 meg Ethernet used lots of them. And
hopefully it only used 2 per string.
Well, yeah, but you had to have them.
Yeah.
I had a bag full of them, I think. If we put this 50 ohm terminator, let me just put that on there. We know we can compare, and the question is a very good question, and it's not a trivially easy answer. If we put this 50 ohm terminator on my little set of adapters here and sweep it over a little bit wider range, I don't know, this is a pretty decent range, I guess. Let's sweep it over a wider range. We should calibrate it. Well, maybe we should just look at this. The size of the dot around 50 ohms is pretty relevant. And you can see that maybe I should turn the marker off. All right, now you can see the little tiny green thing. It's not right at 50, but the little tiny green splotch says that over this frequency range, there's very little variation in impedance. Maybe a little bit. If we put on the first thing I showed was a 50 ohm resistor on a couple of BNC pins, and that's not probably going to be very good at this frequency. But we can quick put that back on there, and you can see. Then we can also put that 50 ohm in connector load on there. There's my, there's my 50 ohm resistor. So it makes a little bit of a line. This is a carbon resistor, probably not a thin film. It's just a cheapy 50 ohm resistor, and you can see the length of that line right here. That's sweeping from 420 to 460 megahertz, but it isn't a dot. So
Also, it looks like it turned pretty capacitive too.
yeah, well, now it's a full length resistor with the leads hanging on it. So it might be a little bit better if I trim the leads off of it. Then it's hard to stick in those little vector pins.
Yeah.
But you're right. It either turned capacitive or it's not quite the same value. And the calibration value we picked might have been closer to 50 ohms, because I used the commercial 50 ohm Terminator, and this is actually, it's a 51 ohm resistor. Let's try the N connector 50 ohm load. I just screw that on. Now, once again, they're not calibrated to anything because what I use to calibrate is none of them. But I'll put on my load. I think a person could do relative measurements. So you could use your best calibration load and then compare that to your other calibration loads and see if it changed the results. And if you picked overlapping frequencies, you could probably help. You know, there's a guy named Larry Bell, and I wanted to tell you this anyway. There's a guy named Larry Benko who has done a fantastic job of YouTube videos, primarily dealing with the Smith chart and primarily using a piece of software called Simsmith. And he has done a tremendous amount of testing of homemade loads and stuff. Now, I don't even see a green dot on the screen there. Should be there.
I'm sorry, what was the guy's name again?
Larry Benko. He is, if you look on YouTube, it'll be real obvious.
B-A-N-C-O?
B-E-N-K-O.
B-E-N-K-O, thank you.
And there's another guy, Alan Wolke, W-O-L-K-E. He is W2AEW. That's Larry's call sign. I forgot Larry's call sign. You guys can meet Malaysia, one of the little dogs I was talking about. She decided that I'd spend enough time not holding her. I'm looking for the green dot. We should have a green dot. Did I turn off that channel?
Hey.
What's a Zoom meeting without either a dog or a kid?
Hey, you mentioned thin film. Can you get some Vichets for ham radio? Do they sell them?
It's possible. One of the Vichet distributors in town is one of my customers. I could ask him.
Yeah. Maybe Mike could send out an email or something, because those are really good resistive loads, and they're kind of stable.
What kind of power output is the VNA for the what rating on the resistor would you need? It's pretty small, but do you have
Yeah, it's on the order of milliwatt. It's real low.
Okay. So you could go with like an old 0603 resistor probably, or
well, that's
something.
what Larry uses. He uses he builds connectors up like the one I showed, like this, and then he'll put a surface mount resistor between here and here, and between here and here. He might use 4 of them, but the spacing lends itself fairly well to surface mount resistors.
Mm-hmm.
And if you're going to do that because of the way resistors work, you want to use something like a 200 or 220 ohm resistor if you're going to split it across that way,
Right.
so that you get your 50 ohms or 55 ohms.
And you'll reduce the inductance by paralleling it. So I think you can get improved frequency response by using a collection of 4 200 ohmers or something like that. Please check out Alan Wolke's work. And Alan has a number of very excellent videos on the VNA. He also has a very excellent set of videos on other ham radio topics and other circuit topics and such. He does a fantastic job, and much less, what would you call it, distracting than mine have been. But he does a great job, and so does Larry. I can show you very briefly what one of the cool things about the Smith chart is that once you're familiar with it, you can take this down here. I'll bring it up so you can see it. From the Nano VNA, you can export an impedance file. And that impedance file is in a format that you can import it into a Smith chart program. So here is Simsmith, and it has the concept of a generator at some impedance and some frequency and a load, and then components down here that you can stick in between the generator and the load, and you can plot either Smith charts style graphs like that, or you can get impedance graphs like that. And I don't want to get into that because it's a deep subject and takes another meeting. But if you want to go into how to use a Smith chart, importing impedance files into it, you can make the impedance file from your antenna in just a few minutes with your VNA, transfer that impedance file as a load, and instead of giving the load a value, I'll show you over here. The load can be a value. In this case, it's set to 50 plus J0. But if you want to, you can create an impedance file, and I'll show you just for fun. I can probably put on there my tri-band dipole. It should be here somewhere. Maybe I don't have it on this computer. Probably don't, sorry. But I have, I've taken a...
Scroll down a little bit perhaps in that list.
It's not there. I had it on my other computer, I think. Well, this might be it. It might be. Yeah, well, okay, it doesn't cover that frequency range. Okay, so it probably goes. Well, I didn't prepare this, and it's obviously not going to work directly. I'll be more than happy to go through this at another time, or with any of you that are interested. But if you make an impedance file of an antenna, especially a multi-frequency antenna, and then import that into Simsmith, and that'll give you the Smith chart for that impedance file. And then you can do stuff like stick matching networks in. You can put a model of a tuner in there and see if the tuner will get you through the right range. Larry Benko has some wonderful YouTube videos on doing exactly that, showing you what range a given tuner will match and giving you information about how to calculate matching networks by putting the components into Simsmith. I mean, this thing is so easy to use. If you want to put in an LC matching network, you just grab the components. Let's put in a series L and a parallel C. And now we have a generator, a C, an L, and a 50 ohm, or no, the load of my antenna. And now if you look over here, it's complaining because I don't have the frequency set right. But there is the Smith chart of that thing, and you can see it actually has almost exactly a 50 ohm match right there. The curve goes through it. The circle is an SWR circle, because on a Smith chart, a constant SWR is a circle centered on the center of the chart. So you can see that this thing is, that's SWR is 1.2 down here. So this antenna is showing less than 1.2 W1 to 1 between these two frequencies, and then outside that range, it's higher. So I know I'm probably boring everybody stiff. So I hope you've enjoyed.
Oh, that's great. This is great.
Thank you. Really good.
I'm more than happy to give you any background information. Look up Larry Benko and Alan Wolke, and you'll have hours of pleasant listening.
I have a question.
Put question away.
Okay. Earlier, when you were looking at either a single or a two-band antenna, you had the frequency set fairly wide apart. If you were looking at a 2-meter antenna, why wouldn't you sweep from, say, 140 to 150?
You absolutely could, and it'll zero you in on that range, and it may be that's what's meaningful, and if so, with your limited number of points, you should narrow the frequency span down as much as you like. Sometimes it's nice to see where it's coming from, and I mean, I've had occasions where I tried to sweep just the peak, and we can put that back on if you like, and we'll put that antenna on. It's sometimes interesting to see where the antenna is out of the band that you're looking at, or the resonance. No, lost my parts here.
Uh-oh.
What you should remember, and a lot of people complain about it too, even with the simple ohm meter, it's been our habit to pick the thing up, zero it, make sure that it's at full scale is on the other end of the scale, and then make it a resistance measurement. And you very frequently have to change the zero depending on how strong the batteries are and stuff. So calibration is just a part of the process, and it really can't be avoided. I'll put that antenna back on. What we could do, if you like, is we could actually take this antenna and scan it over the range of let's say 120 to 400 or to 500 or something like that, a wide range. But then we should be able to see both dips, and that might be interesting, and it would be a reason you'd want a wide span. But we might very well not get enough points in the area where we want to measure it to see much. And so all it would do is give us another area that we'd want to hone in on later. So let's go quickly cal that.
If I remember the VNA settings correctly, or the nano VNA settings, it's only calibrating across 100 points across that range.
The different ones are different. This particular one I'm showing you, it does 201.
Okay.
But that's exactly right. The very limited number of points. So
figure out that what the step is in order to get that number of points across the range. And if the entire range you're looking for on an antenna is between 2 points, you may not see the dip.
You're exactly right. So I'm curious to see what we're going to see right now, because I just set it to start at 100 and stop at 500. Now we're going to go cal it. Reset.
And as a reminder, we're on the screen as opposed to your camera.
Okay. What happened? Oh, I turned that off. I'll close that. and put you back on. Keep losing my mouse.
Not the type of stall you want to try to pull out of, right?
Right. I did. I'm here. That's,
Yep.
you can't see me, but that's me. We had the camera tied looking in toward the airplane out on the strut facing back. And we went up and did some spins and then took pictures doing that. Lots of fun. So did it come up? There it is. All righty. Now I had put that on full screen, right?
Yep.
Okay, so I had already told it the stimulus is 100 to 500.
And you can see those as the start and stop at across the bottom of the screen.
Exactly. I got the open. Now I'm using for calibration loads, I'm using the little SMA ones that come with the Nano VNA. So there's the open. If you look at the green line there, on a perfect open load, it actually should trace around the outside of the Smith chart. So that actually looks pretty good there. All right, there's the open. A capacitor will start and follow the outside of the Smith chart as well. That's a short. So a capacitor will follow that outside circumference. An inductor will start as a short and follow the outside. This short looks pretty decent as well.
The way to think of a open is that you're just looking at the capacitance between the center conductor and the shield.
Absolutely. Okay, we'll throw the load on there. Okay. Now we should see what looks like about a 50 ohm line, shouldn't we? With the load on there. So if we put on our Smith chart, looks like that got off somehow. I had that on the green trace, right? Looks like the green is on. I don't see it though. What's the format of it? It says Smith, so it must be just too little to see. So let's put on the antenna. Yeah, it must have been just a dot. I can see the green lines on there. What happened to my antenna connector right there?
Green dot hidden behind the blue lines.
Yeah, it must have been right there, just a dot, which it ought to be. All right. Now you can see a couple of things. It's got an SWR dip here. That's the 2 meter side, and it's got another one over here.
Could you move it a little bit more in the center of your camera range, please?
Oh, I'm sorry. I'm pointing at stuff and you can't see it. I can see it. All right, so that's obviously going to be our 2 meter antenna. or a 2 meter low SWR point, and that's the 441 over here. Now all this going around and around and around in the green is because one turn on the Smith chart is a half a wavelength. So if we go from here to here, that's a quarter wave, and another quarter wave from here to here. So you got a half wavelength, and that's why in a piece of coax, a half wavelength or a quarter wavelength piece gives you an open or a short circuit in impedance. Everybody unfollow that one? Did I pull a trick on you? Okay, now we got a marker on here. So that should be about, it's about 438 megahertz. If we pull it back here. That's our 2 meter one, 138, 139. You can see we never get too close to the center point either, do we? If that would be our exactly 50 ohm point right there. And the green line doesn't really ever go through it.
Yeah, you're closest at your 440, but not nowhere else.
Well, right now, we are, if you look at the number up above, we're at 61 ohms, 5.95 nanohenries or whatever. And if we go over to here, sometimes dragging it on the yellow line is easiest because that has the fewest number of wigglies in it. You can see that one is right here. So neither one of them are right on. Now, the little jaggies in the curve, those are the points, the calibration points. So it did really pretty well with that few number of points and that wide a frequency range. I mean, it's enough to be meaningful. But in truth, if I were looking at that, I would say, okay, we're going to do a separate sweep for the 2 megahertz part, and we're going to do it from here to here. We're going to do a separate sweep for the 70 centimeter part and do that from here to here and get a lot more meaningful numbers. Anybody want to say anything else?
One more question.
Yeah.
Wouldn't it be important in a real world situation? Let's say you're tuning an antenna on your car. Okay. Wouldn't it be important to do the calibration at the antenna end of the feed line?
Yes and no. The VNA measurements are accurate for the point where you attach it. They call that the calibration plane or the reference plane. When you calibrate it, you establish that point. And so if you want to measure the antenna itself, you should measure right at the antenna. If you want to measure the antenna in the feed line, then you measure it at that beginning of the feed line. When you have a product like Simsmith, you can actually put the transmission line, oh, I shut it down already, but you can actually put the transmission line in as a part of that connection. You can put the impedance file in as the load, and then you can make the length of the transmission line a negative. So if you have 12 feet of RG8 or whatever, you can put in 12 feet minus 12 feet of RG8. And then you can look at the impedance looking through the negative transmission line and model the actual antenna connection. And then that helps if you're going to do something like the antenna is up at 100 feet or whatever, and you don't care to climb up there with your VNA. So you can do it either way. You can adapt your impedance file to take account of the transmission line. Good question.
Yeah, that's great. You know, the Simsmith's a great piece of software, and for you and those other else that are taking notes, a similar program called LT Spice is great for modeling more than just a RF circuit. You can put amplifiers in there and everything else. And that's LT Spice. If you want to make a note of that, if you use that one before yourself, Carl.
Yeah, I agree that I use Spice all the time.
Yep.
And LT Spice is free and pretty comprehensive. And not only that, it comes from Linear Technology, and they do a great job of giving you models for the components that they build. It is very extensible, and there are component models that work in LT Spice for other manufacturers' products. And you can even do your own. I had a stint a year or so ago where I was bound and determined to build some tube amplifiers.
Mm-hmm.
And I put models in of the mathematical models for the tubes. Now, since then, I found some libraries online that were probably better than I could do, but needless to say, you can add models to it. And then one extension, the SimSmith that I showed you, has been superseded by another program. The guy who wrote that is Ward Harriman, AE6TY. And if you go do download SimSmith, you'll get it. You'll get the links to Ward's pages. Ward did some videos on using SimSmith, but really Larry Benko took off and really expanded that. Ward has extended that program now that the NEC products, the antenna modeling products, are public domain. The guy who owned those, and I should know his name. I'll try to think of it, but there was a guy that sold the NEC, Easy NEC products, and he put that in the public domain as much as he could. It's now downloadable, and you can go and download and install a copy of EasyNEC, and it's an excellent program. Ward actually put that in as a front end to SimSmith, and so now you can connect an antenna model in front of SimSmith, and the program is called SimNEC, and you can model the antenna as a part of the SimSmith project, and so you can get a composite, and it's really nice. You got to be pretty sharp to run it, but it's a very excellent product.
That's great. Thank you. That start little and just learn more and build on it and build on it.
Yeah, you got it.
Yeah.
Now, if you're interested, we can talk to Mr. Miller about it, but another session, either on extension of the VNA one, because there's so much more we can talk about there, or another one that might be also interesting is how to use SimSmith, because Smith charts were invented as an aid to calculation. Did a very good job. The math is real messy, and doing it without mistakes and getting good results is difficult. And so the Smith chart, when you learn how to use it, is a way to do graphical solutions of the difficult mathematical stuff. When you use it with a product like SimSmith, it becomes very, very much more, because you don't even need to do the graphical solutions, because SimSmith gives it all to you in excruciating detail, and you can pull out graphs of almost everything you want with a few mouse clicks, and you create your circuits there and analyze them with SimSmith and see the results on either flat charts or the Smith chart. And once you start using it as a graphical analysis tool instead of a calculation tool, it changes completely in value. It's really a wonderful environment, and I'd be happy to do another session on that sometime. But Larry Benko's products, if you just sit down and watch all his videos, you'll be there, because Larry has done a great job.
I have a question about the quality of are there different manufacturers of these devices?
Yeah, the answer is yes.
Okay.
Not a great deal. The manufacturing quality rather than the instrumentation quality is the big variant. I was telling you, this thing that I'm using, the blasted USB connector came right off the circuit board. It actually was not soldered correctly. And it's a micro, which is kind of a weak USB to start with. And that has two little ears that go down into the circuit boards that aren't electrical connections, they're mechanical connections. And those two ears were not heated up well enough to bond to the solder. And so the only thing that was holding it on were the 5 little tiny, 25 mil tabs, and it fell off. So that wasn't a design issue other than the fact that it was not a real great connector.
Are the pads still on your board?
Oh yeah.
Because
Yeah.
I've already done one repair to a micro SD adapter on a Raspberry Pi. So I've got a bunch of those connectors if you need one.
Well, the connector wasn't really hurt.
Okay.
And I was able to solder that to the board, and I got it hot enough so that the solder adhered to the mounting tabs. Where I'm having trouble is the 5 little tiny pins. 25 thousandths is awful small for the end of a soldering iron. And I've had it under the microscope and everything, but I can't get it to connect.
Probably your best tip is to remove as much of the solder, just enough to tin it, and then use a lot of flux.
How you doing? How you doing?
Yeah.
Thank God. Thank God.
Open mic.
Yeah, or a heat gun if you can get in there. I don't know how much room you have, but then you got problems with possibly blowing away other parts.
Yeah, if it got on the other ones, it would make a mess. It's it's modestly accessible, and I can get my soldering on there and touch it, but I can't tell when the solder has flowed, and it's way too tight to be able to dip a little bit of solder on it. I might be able to put some solder paste on it and have it wick into the connection. That was going to be my next try. But it's held up pretty good. It's still working. It's still on. It's been on battery the whole time.
Someone was asking about different manufacturers. I have one which is a Nano VNA H4. There are different versions between V2 and H4. There's also some discussion in a QST that there are some manufacturers that might be clones and not really an actual VNA. So they should all work, but it might be changing about what version you get, just so someone would see this. I don't know if my camera will pick this up or not.
Kind of out of focus, Mike.
Yeah, I know.
Well, they're all clones. Every one of them is a clone. There isn't an official manufacturer of the VNA product. It's individual builders have put it together and they sell it.
Yeah, somebody put together a design and it's been cloned from the design all over the place.
That's exactly right.
Earl, could you hear me?
I was going to say is that if you go to Groups.io, if you're not already a member, that's a really good forum for VNA users. And there's a VNA wiki in there that you'll be able to read a good amount of information about opening things and files and things like that. There you go. And thanks, Carl, for doing this. And maybe we can do another session. We have another member meeting in May, so this might be another one. Maybe we'll do that if we could figure out how to do it in person for once.
Well, thank you, everybody. I really appreciate your patience. I hope you enjoyed.
Great presentation, Carl.